Hello class, welcome back to Anatomy Unplugged. This is the endocrine system, so for my background picture I went with digital 3D surrealism, glands floating in space with some neurotransmitters, sending signals in between. I thought it was kind of fun. Here we go. So how do we review these endocrine glands? If you wanted to challenge yourself and just rattle them off in your mind from top to bottom, name all the endocrine glands in the body, one way to do it is start at the top and go downstairs. Central nervous system, up in the cranium, we have 3 glands. In the neck area, we have 2. In the abdominal area, we have 2. And then in the pelvic area, we have 2. Thymus is kind of thrown in there as quasi part of the endocrine system, but also part of the lymphoid system, which we're going to talk about in the next video. So if you wanted to have a little mnemonic, maybe please help people try practicing their amazing physiology on time. That's the mnemonic that I came up with. If you have a better one, please let me know. Send me an email through the class inbox system or just leave a comment. Now, if you recall from lecture, a lot of these endocrine glands send signals and transmit information to each other. How do they communicate? How do they send the signals? What's the hierarchy? Well, you can think of it as how mail gets delivered. It starts at the Federal Dispatch Center. That picture, by the way, is the Federal Dispatch Center in Brooklyn, New York, where I'm from. This is where I currently live right now. This is the main post office in the city level. That's San Diego, obviously the palm trees there. Then we get mail shifted down to the regional branches. Those are the end organs or the target glands. And then finally, the hormones themselves are the packages with labels. So HPA, hypothalamus, down to the pituitary, and then down to target organs. It's maybe you can think of it as a little USPS mail system in your body. So all these hormones can be quite challenging and sometimes overwhelming. They were for me when I first learned it. Let's get some mnemonics in there. And for the anterior pituitary, I know it might be weird, but I love gardening, so maybe this works for you. I mean, it is hormones. It's all about growth and metabolism. Great gardeners grow greens, tomatoes, turnips, carrots, and daikon perfectly. That last one is a little bit of a trip up because dopamine actually inhibits prolactin, whereas a little bit higher up in the mnemonic right here, TRH does have a weak stimulatory effect, interestingly, on prolactin. Dopamine is a very important regulator. It's also sometimes referred to as prolactin inhibiting factor, or PIF, or sometimes in some texts prolactin inhibiting hormone, or PIH. So hopefully that helps you remember anterior pituitary. How about the posterior? Well, the key thing to remember with the posterior pituitary is there actually is not a direct hormonal portal system. It's really just made in the hypothalamus, and the axons just extend straight down, and they are stored in the posterior pituitary, which just hangs out. And when there is a trigger or message from the hypothalamus that says, okay, we need some of these hormones, namely oxytocin and ADH or vasopressin, they just get released. So posterior, maybe passive and passageway to send those hormones out. In terms of that long list of anterior pituitary hormones, this one's kind of a famous one, I guess sort of famous. Thinking about them as the flat peg, the tropic hormones, which has tropism or a preference towards certain glands. We have FLAT, and then direct acting one is P, E, and G. And E are the beta endorphins. They're often not included in a lot of standard endocrine system textbooks or videos or however you review this, but they are in there. So I do like the flat peg idea because it works. For the table lovers out there, you can make these massive tables. I made this one, which I thought was good because it included the gland, the location in the body to help you remember where it is, obviously what hormones are involved, the target tissue, and then what action it does. So it is a little bit much, but hey, tables work. Maybe there's an easier way to, well, chunk these into different categories. There are a lot of ideas on how to do this. One way to conceptualize this is you got, well, starting at the top, the bosses, and then down to middle managers, and then finally to the independent contractors. So the control center, right upstairs, the hypothalamus and pituitary, we talked about this in class. Obviously, anterior pituitary's got most of the hormones, but posterior pituitary is involved. Then it moves down to the middle managers, which are like your thyroids, your adrenals, and the reproductive glands. And then finally, the I like to say the independent contractors, the ones that are just kind of doing their thing. They're putting in the work. That's pancreas, parathyroids, and the pineal glands. And they are, well, like independent contractors. They don't necessarily need the HPA, hypothalamic pituitary axis, to function per se. Another way to categorize this is by hormone type. If you were a biochemistry fan when you were in school, I loved metabolic biochemistry. It was just really hard. You may better categorize this in your mind from peptides, water soluble, which are faster acting ones, which are your hypothalamic hormones, pituitary, your pancreas, parathyroid, and calcitonin. And then amines, which have somewhat mixed properties. Your thyroid hormones are lipid soluble. Melatonin, your adrenals, epi and norepi, or adrenaline, noradrenaline, are water soluble, but they are amines. By the way, the adrenal medulla, which we're not including in this talk, is actually technically nervous tissue, not necessarily a gland. We talked about that in prior lecture during the autonomic nervous system. And then the third category, steroids, which are lipid soluble and slower acting. So maybe that's another way that helps you to categorize these peptides, amines, and steroids. Maybe water soluble versus lipid soluble, and that funny one in the middle, which has both water and lipid soluble properties, the amines. I like it this way. This worked better for me when I was learning it in terms of how things bind and how things work. The lipid soluble goes right into the cytoplasm or nucleus and makes some actions directly on the DNA often. These are your steroids, your thyroid hormones. Water-soluble ones cannot cross the lipid membrane, so they have to have that second messenger, like cyclic AMP and tyrosine kinase. And these are the peptides, which are a whole bunch of them there, and then the amines as well. So maybe that's another way that you can remember it. It was hard for me to remember the specific metabolic biochemistry, but I like this idea of categorizing them from binding on the membrane versus dissolving in or diffusing in and acting at the nucleus. This one is probably the most fan favorite of students because it's the actual function, what it does, apply this material to the body. Categories of hormones that are involved in metabolism are your pancreatic hormones, cortisol and thyroid hormones, calcium balance, parathyroid and calcitonin. Vitamin D is covered in other areas, renal and dermatology in a way. But you can think of that, throw that in there for calcium balance. Fluid electrolytes are ADH and aldosterone. Reproductive hormones are, well, what you see here. Stress response hormone, cortisone, makes another appearance, so it's involved in multiple areas along with your adrenal hormones. Growth and development here, thyroid hormones make another appearance, and reproductive hormones also make another appearance. So some of these hormones serve multiple categories of function. Oh, sorry, sleep and circadian, don't want to leave out melatonin from the pineal gland. However, this way is perhaps the most well-known or recognized, going down the axis, the three-tiered axis, a trick, so to speak, the HPA axis. There are different versions where hypothalamus, then pituitary, hits a target organ such as the thyroid, we're going to review in this example, where there's this little flow chart, right? Hypothalamus produces thyroid releasing hormone, which then goes to the anterior pituitary, which says, okay, we got to release thyroid stimulating hormone, which then goes to the thyroid, which finally releases the thyroid hormones, T3 and T4. I try to be kind of creative with the icons here. That butterfly kind of looks like a thyroid. The pituitary stalk is what I was going for on this one. And that is clearly in the brain, the hypothalamus. Hits the target tissues in terms of metabolism, growth, and things like temperature regulation, because that's what thyroid hormones do. In terms of the negative feedback loop in red, once you have enough thyroid hormone present, it then circles back and inhibits both TRH and TSH. We have many more of these three-tiered axis tricks here that make it easy to remember. Goes down to the adrenals too. Starts at the hypothalamus, releases CRH, corticotropin-releasing hormone, which then goes to anterior pituitary and says it to release ACTH, which then goes to the adrenals, the cortex, not the medulla. The cortex is an endocrine gland. Adrenal medulla is actually nervous tissue. Adrenal cortex releases cortisol, which goes to the target tissues and helps out with the stress response. Negative feedback loop there, very similarly. Once you get enough cortisol, In the bloodstream, it negatively inhibits release of ACTH and CRH. Our next three-tiered axis pony here is HPG down to the gonads. GnRH gets released, goes to the anterior pituitary, and releases the two hormones, luteinizing hormone and FSH, follicle stimulating hormone, which then goes to gonads, depending on the sex of the human, and releases different sex hormones, estrogen, progesterone, testosterone, which then hit the target tissues involving sexual development and growth and reproduction. The negative feedback, very similarly, negatively inhibit on GnRH, LH, and FSH, except for estrogen, right around the time of ovulation, where it continues to push it higher and higher and higher. You get more and more and more. It's a positive feedback loop, which finally triggers ovulation right around day 14. We do have other axes here that don't necessarily have the three-tiered axis, growth hormone being one of them. We start out at the hypothalamus, GH releasing hormone, and somatostatin too, by the way, which isn't talked about much in a lot of textbooks. Goes to the anterior pituitary and says, okay, you got to release growth hormone. Now this is where we don't have a third step. Growth hormone can act directly straight on the target tissues already. But in addition, it can further act on the liver. That's about as best I could do for an icon that could sort of represent the liver. It's a bit of a stretch there. And it tells the liver to release insulin like growth factor IGF-1. Other tissues can release it, as you can see here, but the liver is the main one. And that is involved in a lot of growth, muscle protein synthesis, and other metabolic processes. So growth hormone has its own axis. It's not this similar to the other ones that we discussed before. Negative feedback, well, very similarly, IGF-1 inhibits both growth hormone and growth hormone releasing hormone. On to the next one. This one's a little tricky, a little different. Prolactin. It does not have a direct stimulating hormone. What happens is the hypothalamus, if it detects a decrease in dopamine levels, and dopamine is a PIF or PIH, as we talked about earlier in the video. If you're a new mother and you're breastfeeding, once that dopamine level goes down enough, tells the anterior pituitary, okay, we got to release prolactin to increase milk production. If you are actively breastfeeding, that also does the same thing in terms of dopamine going down, causing prolactin to go up. So there's this external stimulatory response here, not specifically a hormone in the hypothalamus. This interesting feedback loop, if you can kind of see that here above me, if you recall, there is an additional indirect TRH piece of this. There's a weak stimulatory effect coming from the hypothalamus. It's not considered a strong one. Dopamine is the main regulator in terms of prolactin, but it is there. So if you wanted to, we could add in TRH right there, as I just clicked on there as a way to remember this axis. Okay, on to the next one, ADH. This one's fairly straightforward. We're now in the posterior pituitary. Hypothalamus produces the ADH, goes down the axon, gets stored in the pituitary, and it just releases the ADH going to the kidneys, specifically the collecting ducts, and says, hey, we need to increase water reabsorption, anti-diuretic, no diuresis or no release of water. We need to retain that water, and that increases our blood pressure, and it dilutes our plasma, so it decreases our plasma osmolality when we get more water. Negative feedback, if the osmolality goes down, and so we're sufficiently diluted in our blood, and our blood pressure comes up enough to the point that we don't need to keep retaining water, it inhibits that ADH and allows you to, well, pee out that water again. Okay, and what about the thyroid and parathyroid? Blood calcium maintains a very tight, narrow range, and your body is going to make sure it maintains that range at the expense of your bones, hence the nice little icon there. When blood calcium level goes down, parathyroid hormone gets released from the parathyroid glands. Note, no hypothalamus here. Says, well, we need more calcium, and literally your body leaches or pulls that calcium right out of your own bones to make sure you have healthy and normal calcium levels in your blood. It also increases reabsorption in the kidneys and has some vitamin D effects. What happens when calcium goes up enough? Then your body says, okay, thyroid, now you can kick in, release some calcitonin and lower that bone resorption, get some calcium back on the bones. So yes, unfortunately, your body views your bones as just a reservoir for calcium. It does not care if you get osteoporosis or not because it demands blood calcium levels to be maintained as a priority. Feedback loop here, there's a short circuit, right? No hypothalamus involved. It says we don't need no hypothalamus or pituitary. We are going to handle things on our own. So that's pretty cool. Okay, and the last one here is the pineal gland or pineal gland. This one's fun. Your body can detect light and dark, and essentially when retina senses there's no more light around, it sends a signal straight to your suprachiasmatic nucleus of your hypothalamus. So the hypothalamus is involved, but not the traditional HPA axis that we've been studying. This sends a signal straight to your pineal gland, say, hey, time to release that melatonin to get our bodies to bed. Feedback is kind of fun. You can think of your SCN as a pacemaker. So whenever there's light or dark, your body says time to release melatonin, time to pull it back, let's wake up, let's go to sleep. This is one of the best studied or well-known processes in terms of feedback inhibition in the body. So it's a really fun one. All right, with that, if you're watching this at night, hopefully you're secreting some melatonin and time to go to bed. See you in the next video.